Yes, hello everyone. Welcome to our next MIF++ seminar. Today, Matthew Bright will continue his previous talk and will will focus on applications of two-dimensional lattice invariants. Over to you, Matt.
Sure. Hello, everyone. Hi. Yes, as I say, I'm going to aim to go through the second half of the talk that was planned today, which is about the applications. So if you remember, kind of the story so far we've had is that we've talked about the kind of the general problem that we're dealing with in terms of categorizing periodic structures by isometry and variance, and we kind of went through in some detail and discussed how we've done this for two-dimensional lattices. And it looks like sort of everybody who was here this week was here last week. Well, I can actually, there's a few who aren't, so I will just very quickly bound through this first half. But if you want more detail on this, then the video of last week's talk is up on the web, and also our papers that we refer to. Hang on. In this talk here, so these papers, the Active A paper is a nice summary, and if you want to get into the proofs of things, then a lot of those can be found in Vitali's paper in Foundations of Computational Mathematics. So today, though, we are going to talk about how we've applied this to some real data structures, as I say. So just as just sort of 1 second per slide, we're looking for isometry invariants, a complete continuous isometry or rigid motion invariant, and this kind of diagram explains what all of these things mean in terms of mapping a periodic thing to a space, and having sort of distances in that space. So it's a metric space, and we've kind of done this for lattices. So these are the kind of metric axioms it would have to follow, and we want that distance to be continuous, which it doesn't necessarily have to be. And we've done this for lattices, which you can think of as just represented by some independent basis, linearly independent basis in R2, instead of it all integer combinations. And you know that there's no discrete symmetry classifications of these lattices, but a complete classification up to isometry wasn't until now known. One of the problems with doing that is basis choice. You can always pick a reduced basis, but there are reasons why, as illustrated here, it's difficult to derive a continuous isometry invariant from such a basis. But if you add another vector and create a superbase and demand that it's obtuse, this Selling reduction gives you what you need to know. Gives you the sort of extra bit of information you need to nail this down to something continuous. Last week, I believe, Larry, you asked for a sort of more intuitive illustration of why that's the case. And this is a kind of a picture I've used before. If you can imagine, with this is kind of a reduction which demands that your basis has an obtuse angle between your two basis vectors. And if you can imagine slightly deforming a lattice like this, possibly through some higher symmetry, some square lattice here, say, then as you pass through that, the reduction conditions are kind of, in a sense, going to discontinuously snap your vectors, your lattice vectors, your basis vectors to something sort of discontinuously, and anything you compute from them, this kind of notional schematic isometry invariant is going to work discontinuously. But if you add this extra vector, this kind of illustrates that there's always that kind of, as you pass through this, where the superbase is, or where the vector changes, gives you a kind of stabilizes what the vector looks like. So obviously there is a reflection involved between these two lattices either side of the higher symmetric lattice, but nonetheless the obtuse superbase remains kind of isometric. And you know, you've got all the same parameters. They've just been kind of reflected, muted a bit. So your notional isometry invariant then changes continuously. So hopefully that's kind of an intuitive diagram more than anything else. We've then gone through kind of various numeric sort of algebraic definitions of how you get a root invariant out of that. Essentially, it's the roots of the inner products of the vectors of the Q superbase, and that gives you a point in three-dimensional space. If you care about rigid motions, that is reflections, because the Q superbase is an isometry invariant, but not a rigid motion invariant. As you can see this, then you can kind of double up your three-dimensional space to map lattices of opposite discrete sign. Lattices are the reflections of each other as reflections in a boundary of the space. If you don't care about scaling, you can kind of drop.
Sorry, could I clarify a bit?
Yeah.
So this root products from the previous slide, from that slide and root invariant. So it is an isometry invariant, and it is also invariant under rigid motion. But under rigid motion, it is not complete.
Not complete.
We need an extra sign.
Yeah.
To make it complete. Okay.
Yeah. So we need this extra sign, which tells us kind of what reflection you have up to rigid motion, and you can use that extra sign. Thank you, Dari, to kind of double up any representative configuration space, as it were, of the lattice, so that you can differentiate lattices which are reflections of each other. And as I say, if you want to kind of get an isometry or rigid motion and scaling invariant, that is, if you don't care about scaling, you can drop a hyperplane through this three-dimensional space, and the most geometrically intuitive way to do that is with this concept of the size of a lattice, with some slight other manipulations, you get this nice space which is a right triangle with kind of sides of vertical and horizontal of length 1 here, where your higher symmetry lattices occupy boundaries. And again, you can kind of double up that space with a map by essentially gluing two triangles together across a diagonal. Although kind of notionally you could glue it together across any boundary. This is just sort of make some kind of geometrical sense. And you can get metrics from that just by measuring distances. You just have to be careful to make sure that if you've got lattices of opposite sign, you're measuring distances across all boundaries in the space. This is proven to be not a continuous metric, in the sense it's in fact sort of Holder continuous is the in terms of the expression that we have for it. And you can kind of have a sort of much easier, in a sense, because you don't have to worry about the boundaries. You can have a distance to boundary or a distance to the kind of subspaces representing higher symmetry lattices, and that gives you a kind of continuous measure, what we call a G chiral distance. So it's kind of a measure of the asymmetry of a lattice in relation to particular symmetries. Or if you just want a general measure of the symmetry of the lattice, you can take the minimum over all symmetries. So hopefully that's clear. And in the last talk we gave some kind of definitions of that, and there are plenty of them. With G chiral distance is generally what we call it, but we can define specific ones based on measures in this space. There's a nice geometric map to the sphere, which is slightly more convenient, because instead of your boundaries being kind of across a triangle and you having to measure all of them, this spherical map puts every higher symmetry lattice onto the equator of a sphere, with lattices of negative sign in the southern hemisphere and lattices of positive sign in the northern hemisphere. And then measuring distances then becomes a matter of distances on the sphere, and there's plenty of those. And then we can use the Haversine distance, for example, which is well known to navigators, and then just measure, which is a sort of great circle distance to shortest great circle distance to any other point on the sphere, and use that to determine this hierarchy distance for this particular map. And if we want to kind of then incorporate scaling, we can put the size back in as a kind of height, and then just measure three-dimensional distances to points in the sphere. So to points in R3. So sort of convert these to Cartesian coordinates. And that is a very, very rushed picture of what we're doing. But hopefully this is reasonably familiar. Does everybody want me to quickly go back through anything before I spend the rest of the talk mentioning examples?
So indeed, as usual, we encourage questions during the talk. So you could ask at any time or type in the chat if it's more convenient for you.
Yes.
Thank you.
Yeah, so I'm sort of about to move on and assume that this is all taken relatively as read, as explained last week, and talk about kind of how we've applied this. So the first thing we wanted to do is just kind of fill a big lattice space, have a look at this. You know, we got this continuous space, so we wanted to find a lot of lattices, a lot of two-dimensional lattices. And where can you find a lot of two-dimensional lattices? Well, you can find 3 of them in any 3-dimensional lattice. Well, you can find more than 3, depending on whether you care about sort of isometry and rigid motion and so forth, which order you take things in. But in our case, we just chose a convention of looking at the Cambridge crystallographic structural database, looking for any structure with unambiguous lattice data, because some of them do not have this as an entry, or at least don't have complete entries for it. And we take this length and angle parameters, and by convention, we take 3 triples of these length and angle parameters and use them as our lattice parameters. And then we perform all our calculations. We find the isometrically unique obtuse superbase. We find the and we find all the invariants to see where that to see what that gives us. So obviously there's about 2 million lattices there, well, nearly 3 million lattices really that we're looking at. And this has been sort of seen before on various posters and things. This is what you get. So this is a complete view for the first time of all of those 2-dimensional lattices, 3 million of them, in the quotient square that we talked about earlier. And you can see a lot of things that you might expect. Nature has a preference for high symmetries, and this is reflected by these kind of strong dark lines here. So each pixel here represents sort of about I think it's a point, sort of 0.1 by 0.1 square, and the kind of density, the darkness of the shade represents the count of lattices that live in that square in terms of their projected invariance, their orientation to where projected invariance. And you can see here, so it's very dense along the edges and along the diagonals, because nature appears to prefer higher symmetry lattices, lots of cubics, lots of which is where these will be extracted from. A thing you will notice here is that there's a bit of a gap between this edge and the sort of main body of the map. What we think this is rounding operation. So essentially, if in whatever program is being used to determine the lattice parameters from the crystallographic data, in whatever process it has, will decide when something gets close enough to 90 degrees that it is in fact 90 degrees. And I think we're kind of seeing that there, and that just shows the fact that that our continuity can detect something like that. I mean, obviously, because this is computational, we have to have a cutoff ourselves, because there are floating point errors. So this is cut off at about sort of 10 to the minus 8, based on some background experimental checking of what sort of floating point errors arise simply from computation.
So can I make a comment about what you were saying about the gap? A lot of people, when they see an angle near 90 degrees, and I've seen this recently in proteins where there are mistakes made because they just assume it's 90 degrees.
Yeah.
And especially in the older data, and there's a lot of that in CSD, that they would just, for instance, on film, they would just assume it's 90 degrees, and the structure would be solved wrong. And that's Marsh published a dozen papers about exactly that kind of error. So that gap may actually reflect an incorrect bias in
Yeah.
structural data.
Yeah, yeah. I mean, that's possibly what we are looking at here. So you know, that's already kind of fairly instructive. You see it less around the hexagonal arrangement, and I think we suspect that is because to do. So yeah. So that correction doesn't happen there. It's a bit harder to detect, so you don't get this gap. In fact, actually, this just to make a point, this kind of higher symmetry area is so dense. It's about half of the data set that we've had to plot this density in terms of a logarithmic scale. Otherwise, you would just simply not see anything inside the square. But you can see inside the square, there's a sort of continuous-ish pattern, or rather, there's definitely a pattern. It fills quite a lot of the map. You can see that things quite want to be close to the hexagonal point, which is interesting. You can also see a discrepancy between positive lattices and negative lattices. This is also an artifact. This is because of the order in which we've chosen our lattice bases. Tends to favor the first lattice, the first vector being shorter than the second, on the grounds that in a lot of CSD data, the entry is naturally the lattice vectors are ordered in length.
Can I ask you something, Matt?
Yes.
So if I have understood correctly, you have taken the three-dimensional lattices from the database, and
Yes.
from each lattice, you have generated, let's say, 3 different cases that you examine.
Yes.
That means if I have a monoclinic, that means what I'll have 2 lattices with 90 degrees and
Yes.
1 lattice with...
Which is a
Yeah, and so that means that this is in fact my question. So I'm wondering whether one can make, let's say, any conclusions about the three-dimensional case if you're considering just these, let's say, two-dimensional sublattices.
It is difficult to make conclusions about the three-dimensional case, all but kind of very vague and broad conclusions, which is why we need to extend this to the three-dimensional case, which I will talk about at the end, where there are some complexities. The approach is similar, the spaces are higher dimensional, and there is kind of a slight barrier in terms of the superbase being not as much of an invariant as you quite want it to be without some additional analysis. But I mean, you're right that you know, I think we can broadly pick out a preference for symmetry. I think we can note that the geometry that we picked out in this very large data set, it doesn't exactly fill the space, but this this white space here, really you're getting into very flat, thin lattices of sort, which would be unphysical for some reasons.
Mm-hmm.
Matt, let me help. Yes, Mo is absolutely correct. What we take 3, well, I would say even randomly chosen lattices, 3 two-dimensional lattices from one crystal, from one real crystal. And if our initial crystal has, for example, a primitive orthorhombic cell, then as a result, we get 3 rectangular lattices.
That's it.
3. So you see, high symmetry is even more exposed as a result. So we have more skewed distribution towards high symmetry lattices for that reason.
This is what I was meaning. That means it's kind of, for me, the monoclinic case is also quite, let's say, giving, let's say, the essential point, because it's, if it is a monoclinic, it's not the 90 degrees lattices that are important. That's my point, but of course.
We do have some data sets actually, which we have not, where we've taken, which is possibly a slightly more physical informative thing, where we've taken just monoclinic lattices and mapped out the one two-dimensional lattice that is not 90 degrees, that is oblique. And actually, and you do see a very similar pattern. In fact, I mean, obviously, you don't see you see that things want to be close to hexagonal and kind of thin out as you get away from it. You see again these kind of blank spots. Things don't want to be long and thin for some fairly obvious physical reasons. So yes, you can. I mean that is also, you're right, that are perhaps a more, if we wanted to illustrate something useful about the 3D lattices, rather than, in this case, this kind of early thing is about, let's say, demonstrating computational power on large data sets. We might well kind of show that sort of data as well. The eagle-eyed among you, incidentally, will spot this this little dark dot here. That's oxalic acid, which is obviously an extremely popular thing for testing structural data, or for testing structural data interpretation methods, and therefore the CSD has several hundred roughly similar oxalic acid structures uploaded.
Mm-hmm.
So if I could extend a little bit of what Royce said, that what you see is in part just bias on the way the crystal structures are replaced to some extent. For instance, centered tetragonal lattices can always be done as either face-centered or body-centered, but the body-centered is always the one that's chosen, except in very rare cases. And there are similar things with what you choose as the unique plane in monoclinic.
But these are all selling reduced.
They're also the three-dimensional cells are
the three-dimensional cells aren't, no, but each of the two-dimensional lattices. So each of these is a.
Yeah, but the thing is, if for instance, in tetragonal, if you choose a face-centered lattice versus a body-centered lattice, and then selling reduce the planes, you will get different answers. And the same thing in some of the monoclinic cases.
Okay. That's, yeah.
Monoclinic is much more complicated than that. But yes.
Yeah.
Matt, since indeed the monoclinic lattices so interesting, maybe next time when you give it a talk on this topic, it would be nice to include also a map, continuous map, covering only oblique lattices, two-dimensional, taken from monoclinic crystals.
Yes, yeah, no, and we have that map, so I'll put it in. Yeah, no, because you're right that.
What I'm saying is, and Moise is saying also, I think, that in the monoclinic case, the choices are to some extent arbitrary, and people make different choices sometimes based on the particular structure that they want to compare something to. So,
right. So of course, yeah, of course, all these choices in the three-dimensional case can be properly resolved only by looking at the real three-dimensional lattices.
Yeah, exactly.
At the moment, we are here showing results only for two-dimensional lattices, not yet three-dimensional. But yes, yeah, we understand the problem.
Yes.
So let me, to summarize this plot, let me only add that it was a bit surprising that despite this preference for high symmetry, say 3 rectangular lattices for each primitive orthorhombic crystal, inside, so in this domain in the yellow triangle in generic case, you have 45% of oblique lattices. So despite all preferences, nearly a half of two-dimensional lattices in real crystals are really generic.
Mm. Yeah, and we'll come to talk about how generic they are at the end of the talk when we get to the business of random lattices and that sort of more mathematical question. So to continue, yeah. So a thing we can possibly ask is, can we in some meaningful way relate all of this data to some sort of chemical data? Obviously it's going to be a bit more crude than the actual than the structural data itself. So the PDDs that you may have heard about from Dan's work with the group. But even with this kind of much simpler and invariant, can we see some differences? Might it be predictive of anything? And the answer is sort of not really, but you can see some slight differences which are possibly worth talking about. For example, do heavier crystals, do crystals made from heavier weight molecules behave differently in terms of the symmetry of the two-dimensional lattices you extract from them, to provided you're consistent between the two groups, to lighter ones. And you might, in a sense, think that the lighter, so heavier, so kind of if you looked at this in a discrete way, there's a part of the story you wouldn't pick up, because what you'd see is that lighter crystals tend to be more to be more likely to be in higher symmetry than have higher symmetry two-dimensional lattices than heavier crystals. But there's an interesting, if you can then kind of actually compare the continuous chirality metric, it's not very different, but there's a sense in which kind of higher weight molecular crystals have kind of they have a wider spread, but they want, in a sense, they want to get closer to being symmetric, to being non-oblique, but they can't. Whereas lower weight crystals kind of spread out a little bit more, or kind of move a little bit more occupy a little bit more of the space. So there's a sense in which you might say, I don't think the differences are enough quite to draw this conclusion, but you might ask something like, is the problem with high molecular weight crystals that they sort of want to be symmetric, but because they've got so much stuff in them, they can't, whereas crystals made from lighter molecules, which have less stuff in them, are sort of a bit more flexible about the kind of configurations that they can adopt.
Matt, you might want to look at the work that Todd Yates' group did quite a few years ago about preferences for space groups and preferences for chiral and non-chiral crystal structures.
Yeah. Yes, no. I mean, I think that there are some preferences for lattice parameters and things that I have seen papers about that in the past. Or presumably these were done on discrete chiralities, yeah, or discrete chirality. Chirality is a binary as opposed to a chiral distance measure. Is that right, or is the Yates work? Does the Yates work use their own continuous measure of? Well,
I've not delved into the Yates work in a long time, but the woman who did the work did things that to me were quite unique. So you might want to look back at that.
Okay, I'll go and have a look at that. Do you have a reference? I
don't offhand. I can get it probably, and I'll send it to you.
Thank you. Thank you very much. So the other thing we can look at is organometallic structures, because obviously they're very popular. They're a growing thing that's being uploaded to the CSD. Can we see any difference between organometallics and non-organometallics? And kind of the answer is, again, the differences are very small, but it does look like there is some sort of extreme, possibly some slightly more extreme chirality distance values in organometallics than there are in non-organometallics.
Just a comment. I put the Yates reference in the chat.
Thank you. Great. I shall look forward to looking at that. I've used the spherical metric here just so that you can see how they behave, but obviously the one in the kind of in the quotient triangle would look similar. How are we doing? Half past. Good. So that's that. But obviously, as people have pointed out, and quite correctly pointed out, this is a somewhat artificial way to generate three-dimensional lattices, but it's probably the biggest data set we could find of, let's say, naturally occurring ones that we could pull out. What's perhaps a bit more chemically realistic is thinking about two-dimensional materials, which since people isolated graphene, has been growing because they have they can have these immensely useful properties in terms of sensors and things. This is just an overview graphic from a recent review I found. If you want to kind of delve into if you want to delve into these structures a bit more, there are lots of them. They're not just limited now to graphene or elemental structures, although they form. There are some very broad groups, kind of MX2, where M is a metal, or their transition metal specialized equivalents, certain kinds of oxide and hydroxide. I mean, there are various more exotic structures. But the point is, you can kind of layer these up and have them have kind of really useful thin layer conductivity or sensing properties. So we might be interested in their properties, and there are kind of enough of them now, perhaps, to think about them in bulk. So why would I matter about the kind of chirality or the asymmetry? It's because, and this again is from a review a few years ago, it's because actually it's quite hard to find, and we'll kind of see why in a bit, lattices where the two-dimensional geometry is strongly asymmetric, where it isn't sort of hexagonal mostly, or as it is in graphene, or square. But when you do, there's some immensely sort of useful properties. They kind of behave interestingly under pressure in different directions. So there's a kind of piezoelectric effect. They might have electrical resistivity that's different in different directions, and it's not, or in different kind of orientations of them as layers. And it's not hard to imagine the various ways in which you could usefully apply something like that. So we want to look at lots of 2D materials. And fortunately, we're starting to see lots of these databases spring up. There is some overlaps between them, and they're constructed in different ways. So kind of synthesizing all of them. We found about 4, 2 of which are both large and publicly available. 2D Mappedia is a fairly recent one published in Scientific Data, which is a Nature offshoot. A lot of these are assembled from in synthetic terms. So only a couple of these in the database at the point that I downloaded it, say a couple of months ago, are directly reported from the literature. A lot of them are done via what's called a top-down process. They call this, it's a kind of layer exfoliation. This is a purely geometric, a sort of purely geometric simulation. Essentially in which you look at how topological features, connected topological features, grow as you expand the unit cell, and if you have a two-dimensional connected topological feature, it'll grow as n squared. If you have a one-dimensional one, and so forth. So you can kind of use that to detect whether you're finding a layer in some direction, which may not necessarily be a lattice direction, which is why you do it in this way. And then you kind of simulate, or you simulate what happens using DFT when you peel a layer off, or you try and figure out how you might peel a layer off the bulk crystal structure. Then a further sort of slightly more of these, the other half, as it were, or slightly more than half, are created by doing the same sort of chemical simulation, but this time taking atoms from the top-down structures, atoms from the molecules of the top-down structures, and replacing them with atoms from the same group. So these are all kind of simulated structures, but they're all in there, and they all have a defined two-dimensional lattice geometry. So again, the first thing we do is we kind of put it in the quotient triangle or the quotient square to have a look at what we can see, because we've got 6,000 of these. That's enough to start looking at the square. And again, I mean, a guided tour of this is that you are you know, and again, this is possibly more meaningful than it is in the three-dimensional case, when obviously there are some fairly obvious mathematical reasons why you're going to be enriched in higher symmetric lattices. You can see here that higher symmetry is very popular in both for both the substitution and layer detection methods. So things want to be symmetric, which is as we'd expect. But you can also see plenty of structures which occupy the space of oblique lattices, perhaps a few less. And you can see some sort of perhaps some clear white spaces. This may be of interest to people whose first stop in exploring for new structures in materials discovery is to look at a white space. So one can imagine creating some sort of formal measure of how far a point in the square is away from its nearest neighbors, and using that to talk about the kind of novelty of a structure. So already with this sort of map, we're providing explorers who care about that sort of thing with places to look. Although obviously, again, you can see things thinning out towards this bottom right-hand corner, which, you know, is kind of fairly obviously not physically realistic, because of the kind of configuration of the lattices down there. With sort of, you know, you couldn't fit atoms in something that thin. So hopefully it's clear to everybody what they're looking at there. So the question is, like, how can we use kind of chirality? So remember that we care about finding asymmetric lattices, but we want to be able to make them. We want to be able to make these asymmetric lattices. So what we want to do is we want to look for things that are highly asymmetric, but also there's some indication that they might be stable in two-dimensional form. So what can we do? Well, we can plot. So luckily in this 2D Mappedia, there is some data that helps us to do that. There are a couple of energy measures that we can use. So the decomposition energy is notionally the energy that it would take to pull a molecule apart or to pull a structure apart. So ideally, we want this to be quite high. If it's very low, if it's close to zero, that means this thing is just going to explode. You know, if you can even put it together, it's going to fall apart, possibly quite violently, in its when you try and make it. And then we've got kind of exfoliation energy. Sorry, Larry, hello.
On your right-hand slide, it says CBR3. I think that should be CRBR3.
Should it? Yeah, quite possibly. It's sorry. Well, okay. So we have found, looking at this database, that there are some sort of dubious, certainly the substitutional structures are perhaps realistic only in silico. So I think I found CBR3 rather than CRBR3 here.
Well, it's a little odd because I know that CRI3, which might be the same structure, is a two-dimensional structure.
It is quite possible. Okay, I will have another look at that, because it is quite possible that I have just carried a typo through in my head all the way, especially since it's in this nice area of stability. So yeah, the exfoliation energy is a purely simulated calculation of basically how much energy you have to put in to pull one of these layers away. Typically in the literature, well, I've seen it quoted that you want like about 200 MeV for an exfoliation energy to work, and you don't want it to be sort of negative. And also, typically in the literature, decomposition energy is harder to talk about because it kind of depends on the structure and the solution and the surrounding energy, the sort of context in which you're making the molecule. But you can see here that we've isolated on the left. It is just like all of the molecules which are color-coded by, actually we've used assigned chirality here so that you can differentiate strongly negative and strongly positive chiral distances. And it's kind of rather hard to see these because, you know, lighter colors mean, if I make things transparent, that they are they're not very asymmetric at all. They have a low chiral distance. And we're doing this from sort of D2 here. So we're doing this from kind of centrosymmetric lattices. not centrally, sorry, rectangular centered lattices. But you can see here that kind of this sort of region is a region that we might care about here. We've wiped away everything with chirality distance less than 1. And you can see these nice strongly chiral things, including, so I5N doesn't seem to be a very realistic thing. We've talked about this. This may possibly be CRBR3, but certainly sp2t3, antimony telluride, is both known and known to be a 2-dimensional material. That is, yeah.
So, sorry, but suddenly you start speaking about structures, and I thought that all your discussion is about lattices. So from the lattice to the structure, there is a big, let's say, jump.
Sorry, okay. So I do mean here lattices and asymmetric lattices, yes.
Okay.
Yeah. So finding asymmetry in lattices is this kind of illustrates a possibility of finding these, but these are all kind of. All of these, as far as I understand it, in this, all of these lattice geometries are the lattice geometries you have in the bulk crystal. Sorry, it looks like I've copied those 2 slides. Yeah.
Yes, to summarize this part, Matt, you have started from a database of 2-dimensional materials.
Yeah.
Most of them are simulated, but there are some experimental materials. And of course, from every material, we took only the 2-dimensional lattice, ignoring the motif. So when we compute root invariants of a lattice or with signed root chiral distances, then we consider only the lattice structure without the motif.
Yeah.
Yes. However, with energies were done, of course, for materials, so including all atoms.
Yeah. We
simply combine this analysis, so geometry plus materials.
Yeah, that is the idea. With apologies for rushing through the same slide twice, but I've done somehow. So as I say, all of those are kind of in bulk, as it were. So we're looking at the 2D lattice structure, but we're looking at them in there, but looking at that structure in its bulk crystal, found as a layer. Okay. So what might that do if you do in fact isolate it is answered a little bit by an analysis of this second rather smaller database, the materials cloud 2D database. Again, these select candidate materials from the ICSD and the crystallographic. So this is the inorganic database and the crystallographic open database, COD. And here they do actually simulate, rather than just calculating the exfoliation energy. Well, for some structures, they simulate the exfoliation and then perform additional DFT to say, if I isolate the layer, what does it look like? How does its lattice geometry change? Okay, and so we've got kind of a fewer structures here. We've got a couple of thousand, 1,825. Most of these give you the in situ structure. So, but we've got kind of 200 of them, which give you the relaxed layer structure. So again, just as a quick check, what do all 1,000 or 1,800 or so of these look like in the square? Well, they look like this. The sort of elemental and transition metal ones that you can see here kind of do occupy borders, the boundaries. There are higher symmetry lattices, and again we see a big preference for higher symmetry lattices, but we also see some lattices, some 2D lattices occupying the central space of the quotient square. So we are seeing, at the very least in bulk, in the as kind of layers in the bulk crystal, we're seeing we're seeing lattices of all sorts of chiral distances. We're seeing lattices with different symmetry, with oblique symmetries. But when you do the relaxation, what you see is everything that comes out immediately kind of snaps to a higher symmetric lattice. So all of your relaxed ones, all of your simulated relaxed ones, well, I say all of them, all but 3. Interestingly, live on the boundaries. So and we've got a few here again, where we can see that their chirality distance is going to be a bit higher. None of these, AgNO2 is the only one I've seen reported as a 2D material in the literature so far, but it may be that I haven't seen it. And this again, this is CRBR, BR2 here. So and this just illustrates some points that we've got. So I've kind of separated out some of the different kinds of lattices here. So the question there is so the answer there is, well, in essence, be careful, because even if you think you found an asymmetric lattice, which you'd like to play with in bulk, it may be difficult to isolate that and have it remain as asymmetric as you want it to. So the third bit of the talk, which will be of interest. So this is working with some work of Professor Jens Markloff, who's here today. Hello, about random lattices, because there's a nice question here. Like, are they, we've said in a very broad sense, oh, it looks like kind of oblique lattices are kind of filling the space quite nicely, but what does that actually mean? Are we seeing as a random sampling of all the lattices that there can ever be? And there's this question then of, what do I mean by a random lattice? And it's not as simple, because of the business of kind of basis selection and isometry. That is nowhere near as simple as just kind of randomly selecting two linearly independent vectors in R2, fairly obviously. But this question has been answered by Professor Markloff and others for lattices of determinant 1. So you can express this. So the broad kind of story is you can express these lattices as a matrix whose columns are its basis vectors, and then any change of basis is equivalent to multiplication by an integer matrix. So a member of this sort of well-known mathematical object, the modular group. So this is rather, there's a typo here, which I should have corrected. So a multiplication by an integer matrix of determinant 1. So we can think, in a sense, of a lattice isometry class as a member of the quotient group of kind of determinant 1 lattices by the modular group. So the question we're actually asking is, what does a random distribution look like on that? Okay, and this is just this is a very well-known object. You can kind of it's sort of fundamental domain in R2. I don't want to kind of get too much into the maths of this, but these are a picture of various fundamental domains of it, and how that connects up to our lattices is how a sort of two-dimensional obtuse superbasis is like this. If we scale and rotate a lattice so that either of our 3 superbases are lying along the x-axis at 0, 1, then we kind of, so each, if you do that, then you've got 2 other vectors, and kind of one of them lives in a fundamental domain. So by switching these, by permuting these, you can have sort of 3 points in R2, which kind of represent the lattice. And this sort of fundamental domain should be very you end up with a kind of representation of this fundamental domain from the geometry of the lattices. And then selecting a random lattice in there is kind of, you've got the space and you've got to define some kind of probability measure that is invariant when you under isometry and basis change. I won't go into this because this is Professor Markloff's sort of work, but this is how we've generated it is by kind of this kind of Iwasawa, I believe, this decomposition of a matrix with determinant 1, and then you can kind of generate explicitly. You can compute a random lattice from some point in the interval square between -1/2 and 1/2, interval cube, with a sort of very simple computation, and that gives you the random lattice. So the question then is, if I map my lattices to a fundamental space. And in fact, because it's kind of slightly more familiar mathematically, we map it to, we kind of essentially move this half of the domain across here, because you've got the same fundamental domain basically repeated. Does it look the same? And on the right here, you've got randomly generated lattices, and we kind of put them because they obviously fill the space, and it's kind of, it gets rather hard to see. This has been cut off at y = 5. So this is the height. So if you imagine this is the kind of distribution of the heights of my lattice points in this fundamental domain. So the kind of density of these vectors in this fundamental domain, and you can see here that for this is the kind of random distribution, as it were, and this is our distribution for the CSD two-dimensional lattices. So there's been a bit of a slight crush of the x-axis here, and you can see again these lines represent all your these solid lines represent all your higher symmetry lattices, and it doesn't kind of look very similar with these higher symmetry lattices in, because obviously there's a kind of very strong preference for that. But you can see the you can see the bias towards positive rather than negative lattices in terms of their sign by the kind of lower density in these regions here to these three regions, which you obviously don't see in the random distribution. But if I take away those higher symmetry lattices, so if I look only at oblique lattices, again you see biases towards positive and negative, but beyond that, sort of visually, you start to see something a bit similar. Obviously, there's less of because the higher you get here, the longer and thinner lattices get. So this represents the white space in the bottom right-hand corner of our quotient triangle. And this is yeah, but you can see some kind of visual similarities, which we can kind of sort of test whether or not by essentially integrating across straight lines here. So what is the density at a certain value of the y coordinate of the fundamental domain here? So that's the kind of next thing we wanted to do. And that's the kind of next result that we have. So remember, this kind of height of the second vector is what we're looking at in angstroms, and this is with this is the comparison between Haar random lattices and the CSD, and in terms of density rather than necessarily absolute number. So this is a proportion, I think. What is this number of? No, this is number of lattices, and you can see here with oblique lattices. This is you can see the clear differences here. These sort of bumps represent where we're getting higher symmetry lattices enriched. So what happens if you take them out? Well, it looks a little similar. What you don't get is a distribution of lattices here in this sort of region, but you can see some sort of similarities in where the peaks are. So we haven't done any sort of formal comparison of this yet. But I would say that given if you think about what we're doing, okay, if you think about the fact that we're taking these kind of naturally occurring lattices and comparing them to a completely mathematically random distribution of lattices, we weren't expecting them to be this similar at all initially. But the more we look at it, the more we see that there are some similarities here. That the naturally occurring lattices perhaps occupy more of the space of all lattices than we would expect.
Matt, can I just check the normalization? So both histograms have the same total number of lattices, or?
They have the same total number of lattices. Yes, I've generated the same number of lattices.
But it doesn't look like it, does it? Particularly on the second one, this one.
Okay, so these are again cut off at 5. Basically, you get a huge number more. So in for Haar random lattices, you kind of get a very, very long tail.
That's true.
in these in these distributions. So that's I think what we're seeing.
Okay, thanks.
Okay. So we can pursue this more you know, this is a thing of interest, and obviously when we get into three-dimensional case, we'll want to pursue this in the three-dimensional case as well, because it's kind of a very interesting question of whether kind of nature occupies the space of all three-dimensional lattices. So what can we do next? Well, one thing we could do in the two-dimensional case is, it can't have escaped people's notice that if we've got a punctured sphere, we've kind of got a plane. We've got a very natural projection. And then we can kind of think about what a reasonable metric is on that. So if we want to, and then, you know, the plane is nice because it's a complete metric space in a certain sense, if we've got the right sort of metric, which we would need to check. But rather more importantly and practically from the point of view here is we want to talk about extending this to 3 dimensions, where we've got a kind of slight problem because of two superbases are not isometry invariants in quite the same way. The approach holds. This is an example of two superbases of a primitive cubic lattices that are very clearly not isometric, but both represent the same lattice. So we need to have some more careful metric definitions and look over kind of, essentially we need to look over the different kinds of non-isometric superbase, which are still a finite number. So we need to start working across that. So, to summarize the first thing, to summarize the first talk, we've got a map from the set of all 2D lattices to any space sort of that's kind of topologically equivalent to the punctured sphere, whether that's a square with a point missing, or an actual punctured sphere, or some projection to the plane. We can induce from that a continuous metric between lattices, provably continuous lattices, which we can then kind of generalize to this idea of a G chiral distance, which is a distance to subspaces representing non-oblique lattices. So we then have a nice, we have essentially a continuous measure of how asymmetric a two-dimensional lattice is. And this allows rapid investigation of real-world lattice structures. And what we've seen today is that the differences in chemical properties can give rise to detectable differences in chirality distributions, albeit small ones. We can use this as an approach for 2D materials, isolate kind of possibly stable and strongly asymmetric lattice structures, and show how symmetry changes, sort of answer some questions like that. And we can kind of use this to compare the kind of continuous space, the lattice. We can use this to compare in some continuous space lattices from the world and lattices generated at random. And you are very welcome to try the code, which can now generate random lattices. It can map lattices for you. It can create all these invariants, put them in whatever map you like at the GitHub.
Okay, thank you very much, Matt. Let us thank Matt, please. Okay, I am stopping the recording.